Good morning. My name is James Moore, and I'm currently a graduate student within the Department of Geography at Virginia Tech. Today I'll be presenting the evaluation of spatial representation techniques in determining tornado event frequency within the Central Appalachian subregion. This research is in direct support of my thesis and being presented as a final project within my GIS application and natural resource management course. Tornadoes are an extreme and deadly weather phenomenon defined as a narrow, violently rotating column of air that extends from the base of a thunderstorm to the ground. On average, it is believed that 1,200 tornadoes hit the U.S. each year, which accounts for over 90% of all yearly occurrences around the globe. U.S. tornado records only date back to 1950, but there are reports that date back as early as the 17th century. One common misconception that is often brought up in our area is the statement, tornadoes can occur in the mountains. As noted above, this certainly is a myth. While tornado occurrences are much rarer in complex terrain, they can and do occur. This study focuses on an area along and on either side of the Central Appalachian Mountains where a pretty evident data gap in event frequency is present compared to the rest of the country. The hopes are, by defining a region not based on arbitrary boundaries, but rather similar physiographic characteristics in a noticeably smaller area, smaller scale trends will become evident. Temporally, similar trends are clearly evident when comparing both the regional and national databases, as seen at both the yearly and seasonal scales. Albeit, there are noticeable differences in event count and overall percentages when comparing the injuries and fatalities that are directly contributed to the events. It is important to note that there is quite a bit of uncertainty when it comes to tornado occurrence data. Overall, this project will be broken into two tiers. The first being a determination of the best spatial resolution representation for the tornado track data. The second will focus on determining the most representative interpolation or density calculation technique when processing and presenting the data to its users. A national representation of tornado impact frequency at a 25-kilometer resolution is shown above. As mentioned prior, there's a noticeable lack in occurrence data in our study area. However, when teasing out the rest of the country, higher impact areas originally shown as moderate to low impact frequency are highlighted. The main considerations when discussing resolution are data storage, data validation and accuracy, overall prettiness, aka would an emergency responder be able to use and understand it, and finally is the rule of thumb followed, which is defined as resolution grids should not exceed the number of observations present. If so, there will be lots of blank space. 3 different resolutions were compared in this study, including 2.5 kilometer, 10 kilometer, and 25 kilometer grid cells. Each were compared to determine the best representation of the data. The 2 uppermost tiles represent a fishnet grid cells that were created across the study area, and the resulting zonal statistic frequency counts below. Overall, as resolution improved, the appearance of each product improved. However, the overall data representation at the 3 highlighted areas remained the same, with only minor location biases present depending on cell size of the resolution. In direct comparison of the higher resolution products versus the lower resolution products, the lower resolution wins the data storage battle, as less pixels require less data storage needs. When comparing data validation and accuracy, however, there are pros and cons for each. Lower resolution includes larger areas, which may skew over areas of lower frequency. While higher resolution is more precise, a greater number of pixels require a greater amount of interpolated space on the map, which is a potential source of error and discrepancy. While higher resolution images are prettier and easier for the user to interpret finite areas, the smaller grids outnumber the data points, which leads to greater error and misrepresentation. Overall, a lower resolution area of 10 to 25 kilometer grid cells would be best to use. Now switching focus to the types of interpolation techniques, 3 techniques will be compared for accuracy and overall tool usefulness. These will be zonal statistics, kernel density, and line density techniques. To split the difference, a 10 kilometer resolution will be used for this comparison. Visually comparing all 3 techniques with the control group, all represent the high, low, and medium frequency zones well. The resolution seem very fine on the 10 kilometer zonal statistics, while there is plenty of smoothing in both density calculations. Precision seems higher on the line density calculation, as it seems to correspond and follow the tornado track clusters a bit more closely. Now comparing the same 3 techniques to an optimized hotspot analysis performed based on incident starting points, all 3 areas of interest seem to line up similarly. It is quite surprising that a larger hotspot isn't evident in the southeastern corner of Tennessee. However, that may be due to the differences between the use of event frequency and starting points in our evaluation. Taking a look at each tool's function and topology, when using the zonal statistics toolset, each time a tornado track with a user set radius passes through a grid box, that box receives a count of 1. It's a very simple technique with no interpolation needed, but highly resolution dependent and doesn't take into account the length of the track passing through the grid box. Both line and kernel density techniques are similar, with only a calculation difference for each grid box. Line density calculates a grid cell's value based on the presence of the tornado tracks within a common area around the cell. Kernel density, on the other hand, is based on the distance of the cell from the track itself. In the end, both higher and lower resolution techniques could play a role in this research. Lower resolution, while not as visually appealing, will be more of a use to us in the processing phase, as it should eliminate most of the potential error and uncertainty. The line density interpolation also seemed to be the most beneficial technique spatially, as it compared better to the control group compared to the rest of the techniques. In the future, my goal is to further break down the study region into smaller areas. By doing so, we should be able to reduce the resolution without increasing further bias. This should also highlight smaller scale trends and patterns both spatially and temporally that would be helpful to local emergency managers and decision makers. Thanks for attending. I'd be happy to answer any questions that you may have.